Today I would like to solve problem example 3.9 from chapter 3. This problem. Okay, here I have the metric version of this problem. Here we have a shaft with diameter of 40 millimeter, which is shown here, with two pulleys at location B and C. Pulley B diameter is 100 millimeter and diameter of pulley C is 200 millimeter. And as I mentioned, the diameter of the shaft is 40 millimeter. These two these two pulleys are fixed to the shaft by using key. In this problem, we are requested to consider bending and torsional stress only. That means we can ignore the shear stress due to the bending, because normally shear stress due to the bending is much smaller compared to these two stresses. Then we need to determine the location and magnitude of the greatest tensile, compressive, and shear stress in the shaft. Okay. To do this task, first we need to make a load analysis on the shaft to find the location of maximum moment on this shaft. As you can see, this shaft is supported at location A and D. For example, there is two bearing at this location. That shaft is able to rotate around its axis X. Okay. As you can see, on each pulley we have two loads. Normally when the pulley is turning or driving by a belt, there is two sides of the load. One side we have maximum tension and in another side we have minimum tension. Here is 900 Newton and here is 4.5 kilonewton. This should be correct, 4.5 kilonewton. And here again we have maximum tension and minimum tension, 2250 and 450 Newton. As you can see, the direction of these two loads is in Z direction and these two in Y direction, and the shaft axis is Z direction. So we have here a 3D problem, and we need to analyze this shaft in two different planes. One time we have to analyze in plane X, Y, and another time we have to analyze on plane X. Okay, let me demonstrate how we can do that. First, we need to draw the free body diagram of the shaft in XY plane. Okay, as you can see, in XY plane we have these two loads, which they are in Y direction. So if you want to substitute the resultant load at location C, because these two loads are at the same direction, so we have to add these two values to get 2700 Newton in Y direction. Next, I have to write two equilibrium equations. First, the summation of moment around point A should be equal to 0. Then the moment of 2700 times this distance should be equal to the moment of reaction load at location D times 2 this total distance. So 2700 times half meter should be equal to dy, the reaction load at location D in y direction, times 0.75 meter. And then we will conclude that the reaction load at location D in y direction equals to 1800 Newton. The second equilibrium equation, we can write that sigma Fy equals to 0. So Ay, the reaction load at A, minus 2700 plus dy, which was 1800, should be equal to 0, and then we will conclude that the reaction load at Y equals to 900 Newton. In the next step, we have to draw the shear diagram, the diagram of shear force for this plane XY. Okay, in order to do that, we can follow this step. First, I will write down here the AY, which was 900 Newton, and DY 1800, correct? And if I draw a diagram here, X, shear force V in terms of Newton. Okay, at the beginning of the shaft we have 900 Newton. So we start here 900 Newton, and we will continue to the next point. Since there isn't any other load here, again we can continue up to the next point. At this location we have negative 2700 Newton, right? So 900 minus 2700 Newton equals to negative 1800. So we should draw a line from positive 900 to negative 1800. And then I should continue up to the next location. In next location, negative 1800 plus positive. This time, this load is in positive direction, so equals to 0. And then I will draw a line to the 0. So this is our shear diagram. Okay. It's better that always we draw this diagram under each other. Okay. In the next step, I have to draw the moment diagram. It's better I draw below this diagram. I will draw here. Okay, to calculate this moment diagram, I have to calculate the area under the shear force, because the integration of shear force, let's say from 0 up to the 500, equals times dx equals to m, right? So I have to calculate this area. To calculate this area is easy. 900 times 0.5 from here to here, which is 450 Newton meter. Okay, so I have to draw a line. Here is 450 Newton. Okay, so I will draw a line from 0 to positive 450 newton. As you can see, the slope of the line is positive because the area of the shear force is positive. And then I have to draw a line with positive slope. Next, I have to draw to calculate this area 1800 times 0.25 again equals to 450. But this time, because the area is in the negative part of the diagram, so I have to draw a line with negative slope and it will come back to 0. So this is the moment diagram of XY plane. Here is location C, right? Here we have location C, and somewhere here is location B. Okay. Later I will come back here again to calculate this location moment at location B. Okay. Now I want to find the moment at location B in XY plane. So as you saw, we draw the moment diagram first, and here we had uh, 450 Newton meter. Okay, to find the moment at location B, here is location B and here location C, I can use these two similar triangle. That means, for example, if I call here O, the triangle of OC, let's say we call here A, the triangle of OCA similar to triangle of OBD. Okay, so in these two similar triangle, the side of CA is similar to side of BD, right? And BD is actually the moment of point B. So CA 450 similar to moment at B or BD, that means the value which is we are looking for, and this side of triangle, the biggest triangle, this side OA, which is 0.5 meter, similar to this side of a small triangle OD, which is 0.25. And then we will conclude that moment at location B equals to 225 Newton meter. That means this value is 225 Newton meter. Okay. Similar to previous plane X1, now we can draw the free body diagram for plane XZ. Okay. As you can see, let's return back to the problem statement. In plane XZ, these two loads are in direction of positive X. In direction of positive X, right? So if I call that X, Z, right? I can draw this the shaft, and the total force at here 4500 plus 900 equals to 5,400 Newton. Then again, I can write equilibrium equation for point A. Sigma MA should be equal to 0. Then 5,400 times this distance should be equal to uh, dz, the reaction load at location D, times 2 total distance. It's better we write in this way. Let me write in another way. We can say that 5,400 times 0.25 plus dz times 0.75 should be equal to 0. It's better we start to write in this way first. I consider dz as positive direction. If later we found that dz is negative, that means our first assumption direction was right. Okay, as you can see, we found dz negative. That means the direction of the reaction load that we assumed first is wrong. That means it is in this direction. Okay, later we can write again sigma fz, the equilibrium equation in z direction should be equal to 0. So az, the reaction load at location A in z direction, plus positive 500 5,400, and plus dz, which is negative 1,800, right? So I have to write az plus 5,400 minus 1,800 should be equal to 0, and then we will find that reaction load at location A is negative 3,000. That means again this assumption was right, and in the actual direction is this, and equal to 3,600, and this one was negative 1,800. Okay, similar to xy plane, again I will draw the shear diagram, and at location A, as you can see, we have negative 3,600, right? We will continue up to the location of next load. Then we have positive, okay, negative 3,600 plus positive uh, 5,400. 5,400, right, equals to 1,800 positive. Okay, so I will draw a line from here to 1,800. Then I will continue again up to the next load, which is reaction load at the end of the shaft, and equals to negative 1,800. So I will draw, right, positive 1,800, positive 1,800 minus 1,000. Okay, again, if we will return back to 0. Great. Next, I need to draw moment diagram. As you remember, again, similar to previous plane, I have to find the area under the diagram. So 3,800 times 0.25 equals to 900 Newton meter. Okay, as you can see, the area is under axis x. So we may think that we have to draw a line with negative slope, but it is not correct. The reason is moment is the result The moment is result of vector multiplication of x-axis, for example, to zx. Let me write it in this way. As you know, the vector multiplication of vector of I times j. Okay, we can write in this way: I, j, k. I times j equals to k. K times I equals to j if we rotate in this direction. And the results are positive. So let me write in this way. Okay, j times k is positive I, right? And k times I equals to positive j. But if we move in reverse direction, that means k, for example, k times j, or j times I, or I times k, the result is negative, right? Means I times k is negative j, k times j is negative I, and then j times I is negative k. Now we have to see the direction of this shear and x. Okay, so here we have positive, correct, positive x. That means, let me write in this way, 0.25, which is this distance in positive I direction, times this is k, because this is zv in z direction, right? So negative 300, 600, right? 3600 in negative k, right? Negative k. I times k, we have to find I times k. I times k equals to negative j, right? So the result of I times k is negative j. But as you can see, also we have a negative here. So negative times 2 negative will be positive. That's why the result of this is, I wrote somewhere here earlier, right? Is 900 j, positive j. Okay, I will repeat one more time. Here we have positive x, so we will write 0.25 I times negative 360 k. Actually, here I should write only one negative. I shouldn't write two, because I already write one negative here, right? Negative 300, 600 k. And then I times k is negative j, and here also we have another negative, so the total result is positive j. That's why we have to draw the moment diagram with positive slope. Although this area is under x, but the line of the moment should be drawn with positive slope to 900. Okay, next, let me write the next one. In the next we have 1000, sorry, here is the area is 0.5. Let me change the tool. Okay, 0.05 meter times 2. this time is okay. This is I 180 K. So as I told you, I times K is negative J, right? So is 900 negative, negative J. Therefore, I have to draw a line with negative slope and comes back to 0. Okay, here is point B and here is point C at this location. Again, similar to previous plane, I have to find the moment at location C. And again, I need to use these two similar triangles. That means this big triangle and this small triangle. Okay, so in this big triangle, this side of triangle similar to this side of a small triangle, and this side of big triangle is similar to this side of a small triangle. So 900, this side of big triangle similar to moment at point C, and this side of triangle, which is 500, similar to 250 millimeter this side of triangle. So I can find that moment at location C is 450 Newton meter. Okay, now we found the moment at location B and C in plane XY and the moment at location B and C in plane XZ. Now we have to find the resultant moment at these two locations. Okay, so that means I have to find the resultant moment of location B at plane XY and plane XZ. Here in plane XY, the moment at location B was 225 and here was 900. Okay, so the 225 square plus 900 square. The root of this summation is the moment 927, and also we will do same action for location C, and we will find the resultant moment at location C. So if you compare these two moments at these two locations, you can see in total the moment at location B is greater than moment at location C. As you can see, MB is bigger than MC, right? Okay, so next we need to use this moment to calculate the bending stress and to calculate the bending stress. Okay, since moment at location B is greater, so we call location B and critical location, and therefore we need to calculate bending stress and torsion stress at this location B. Okay, so next I have to find the bending stress at this location. As you remember, similar to previous problem, we find the bending stress by using this equation, and therefore uh, for a circle cross section, the second moment of area can be found by using this equation. So when we substitute I to here, then we will simplify it in this way. Then I will substitute the magnitude of maximum moment at location B, and as I mentioned at the beginning of the problem, the shaft diameter is 40 millimeters. So we will convert to meter and substitute here. So as you can see, the the bending stress, which is at the x direction, equals to 147.7 megapascal. And we don't have any axial stress in y direction. The bending stress is only in x direction because the shaft itself was in x direction, or the shaft axis was in x direction. Okay. Next, I need to find the torsional stress due to the torsion. Okay, so as you can see in this equation, to find the shear stress of torsion, I have the value of the torque, right? To find the value of the torque at these two locations B and C, I will draw the free body diagram of each pulley separately. Okay, so pulley B, as I told you, we have the belt with the maximum tight side, and the another side of the belt is loose or with minimum tension. Okay, so definitely the resultant of these two load cause that this side of the pulley, right, because it has greater tension, this side of pulley will rotate, sorry, will rotate the pulley in this way, right, because we have maximum tension here. Okay, so then to find the torque, I have to multiply this load or the resultant load times to the radius of the pulley. The diameter of pulley was 100 millimeters, so the radius is 50 millimeter or 0.05 meter. And then 4,500 minus 900 to find the resultant force which caused to the rotation of the pulley. Then we will get the torque at pulley B is 180 Newton meter. In similar way, we have the tight side of the belt here and the loose side of the belt here. So the pulley will rotate in this direction. And the diameter of pulley C is 200 millimeters, so the radius is 0.1 meter, and times 2 the resultant load, again equals to 180 newton. Actually, as you can see, the torque at pulley B and pulley C are equal, but in two different directions. That means the power at point B will be consumed at location C, or in vice versa. You can say that the input power, one of them is input, another one is output power. The power which will be inputted to the shaft will be consumed in another location. Okay, so because torque at these two locations is equal, again we will refer to location B because moment at location B was maximum. So still we can say that the critical location is location B because torque at these two locations is equal, but moment at location B is maximum. So I will substitute torque here, which is 180 Newton meter, and the second polar moment of area J, again you can find from the appendix, equals to this, and we will substitute and simplify the equation in this way. And therefore we will find that the torsional shear stress is 40.3 megapascal. And the direction of the shear stress is in xy plane, tau xy. Now I have found the axial load sigma x, right, due to the bending, and shear stress due to the torsion. In next action, I have to find the principal stress. So I will use Mohr-Sekel theory equation. Then I will substitute sigma x, sigma y was 0, sigma x y, sorry, again, we substitute there, and tau xy due to the torsion, right? After we substitute this value into the equation, I will find these two principal stress equals to 149.1 megapascal and negative 1.37 megapascal. Also, we can find the maximum shear stress by using this equation again from our circle, and the maximum shear stress or principal shear stress is 75.2 megapascal. Okay, so here is the end of this example.